Bam! Mr. True. In this video, I'm going to work through 6 examples involving tangent lines and how they relate to circles in geometry. A tangent line is a line that touches a curve at only one point. Now, in the video I'm going to focus, this is an introductory video to tangent lines for geometry, so all of our examples again are going to be dealing with circles, and a lot of examples are going to be involving lengths of segments and Pythagorean theorem to work with this right angle relationship. If we were in Algebra 2, I might be doing a lot more work with actually the equations of these lines, and if I was in calculus, because this idea of tangent lines repeats many times through your math courses, depending on how far you continue on, it will continue to show up over and over again. And in calculus, the tangent line, again, the fact that it only touches a curve at one single point, with an idea, understanding of the equations of lines and this new concept you learn in calculus of limits, you'll be able to find the slope of a curve at any given point, which is extremely powerful. But without that idea of limits, the slope, we can't really find the slope of anything other than a line. So geometry, Algebra 2, when you get into maybe analysis of functions or pre-calculus, even in pre-calculus, almost the entire course, you'll only be able to find slopes of straight lines. But in the end of pre-calculus and in the beginning of calculus, you learn this idea of limit, and you really see a powerful tool or a powerful way of using tangent lines that will, again, you find the slope of this tangent line, then you find the slope of a curve at a particular point. And that's really cool because the slope is constantly changing in a curve depending on what point you look at. But this is only geometry, so again, let's just back up a little bit and get the basic idea down. Again, it touches a circle, or any curve at one point. We're going to be talking about circles. If a tangent line, or if a line is tangent to a circle, then it is perpendicular to the radius at that point of tangency. So I have a tangent line. I know it's a tangent line because we're only crossing once. If it crossed twice, then the segment connecting those two intersection points would be called a chord, not a tangent line. The slope of this radius was 4 over 1, so up 4 and over 1. Then at that point of tangency, with the tangent line coming through and intersecting at that point, the slope of the tangent line would be the opposite reciprocal. So if the slope of that radius is 4, the slope of this tangent line would be negative 1/4. You would find the reciprocal of the slope and then change its sign as well. So slope of 1, slope of negative 1/4. That would be really important and useful when we start dealing with the equations of lines of the radius and of the tangent line, but you'll be doing more of that in Algebra 2. Right now, again, we're going to be doing a lot of examples about segment length and Pythagorean theorem. If a line in the plane of a circle is perpendicular to a radius at its end point on the circle itself, then the line is a tangent to the circle. So if I come through here and I draw a line that's perpendicular to the radius, that doesn't automatically mean it's a tangent line. It has to be at the end point of the radius right on the circle itself. So this is basically just our original theorem of tangent lines, and the converse is true as well. Okay, so our first theorem here, our next theorem, if two tangent segments to a circle share a common endpoint outside of the circle, then those two segments are congruent. So I have circle O, I have a point of tangency A and a point of tangency B, and I have a common point outside of the circle. Well, if we have a tangent line making a tangent segment AC and another tangent segment of BC, then what it's saying is that tangent line slash segment, tangent line or segment specifically between B and C, and with a common exterior point of C, then AC is congruent to BC. And they have to say a tangent segment and not a tangent line because we can't measure the length of a line. Or raised, the length is infinity, it goes on forever. So we're talking specifically between the tangent point and this common external point. And I'm not going to do the two-column proof for you, but it'd be really, really easy to prove this if I just simply accept the fact that the radius and the tangent lines are perpendicular, as told to us by the beginning definition slash theorem in this section. If I drew a common segment of OC, then I would have two right triangles that shared a common segment. So OC would be congruent to OC by reflexive property. And a circle is a set of all points that are equal distance from the center. So segment OA and segment OB are both going to be congruent because they're both the radius is within the same circle. So I could prove these two triangles were congruent with hypotenuse leg, and thus the corresponding parts of congruent triangles are also congruent. So I just verbally did a two-column proof, even though I said I wasn't going to. So we want to solve for x. Well, look at what we have in here. And I already have it marked that these are perpendicular, but you really should be able to do that on your own now, understanding that when you have a tangent line or segment, that it is going to be perpendicular to the radius at that point of tangency. So even if I left those out and said, here's a diagram, solve for x, you might go, well, that's a quadrilateral. ACBO is a quadrilateral, and I don't have enough information. And like, yes, you do. The radiuses in those tangent lines are perpendicular. So, if you remember that the interior sum of a quadrilateral, a four-sided figure, is equal to 360 degrees, and you can do that by remembering that the interior sum, or the sum of all the interior angles, is n minus 2 times 180, or just simply the number of triangles can you draw from, pick an angle, draw as many diagonals as you can. Oh look, I can only make two triangles. 2 times 180 is equal to 360, or 4 minus 2, which is 2 times 180 is equal to 360. So this is pretty simple. It's just going to be 360 degrees minus the 90, minus 37, minus another 90, and you solve that for x and you're going to have your answer. Now, 90 and 90 is 180, so 360 minus 180 is going to be equal to 180. Can't believe I just had a pause so long to figure that out. Minus 37. Well, 180 minus 30 is 150, and 150 minus 7 is 143 degrees. And that is going to be what x is equal to. Let me just check my own answer. And yes, it's 143. Let's pause the video, not the tape, the video, and get a couple more examples up here. Given that segment AB is the diameter of circle O, and AC is tangent to, I guess I need to put a segment here, tangent to circle O, solve for x. Okay, so, well, let's see. I don't have it marked on this diagram like I did in the other example, but if AB is a diameter, then OA is a radius, and that means that angle OAC or BAC is going to be a right angle. And remembering that the interior sum of a triangle, one more time, is 180 degrees, this is actually a pretty simple question. All we have to do is 180 minus the 90 from the 90 degrees at our point of tangency, minus 49, and we'll have our answer. Well, 180 minus 90, of course, is 90, and 90 minus 40 is equal to 50. And 50 minus 9 is equal to 41 degrees. So there you go, that's the answer. And if you want to make sure you're right, just make sure that 41 plus 49 plus 90 does actually add up to 180 degrees. Depending on your textbook, I might be a little ahead of you on this, or I might be just reviewing an old concept, not sure. But what is the measure of arc AD? This segment right here. Not segment, excuse me, this arc, this length of distance around that portion of the circle. Well, the measure of an arc, excuse me, I'm not doing arc length, I'm doing the measure of the arc, the number of degrees. I got a little off track there. So the measure of your arc is going to be twice as large as your inscribed angle. Now, an inscribed angle, if it hasn't been in your book yet, is an angle whose vertex is on the circle itself, and then there's an angle that extends from that, and the measure of that inscribed angle is half the measure of the arc. Or, the other way around, if angle ABD or ABC is equal to 49 degrees, then the measure of the arc AD is going to be twice that. So it's going to be 2 times 49, and 2 times 50 is 100, but it wasn't 50, it was 49, it was 1 less. So 1 less, I said 100, so it's 99, and 1 less again would be equal to 98 degrees. And let me just double check. Yes, excellent. Okay, over here, again, we can just assume that we're talking about radiuses and tangent lines. So given the fact that we have this tangent line, and the segment from the point of tangent C to this point out here from the outside of the circle is a length of 8, we have a radius of length of x, and the distance from the circle to this point out here is equal to 7. Now we need to use that information to solve for x, the radius of the circle. Okay, well, I put the right angle here. I could have left that blank and said the radius, and this was an actual tangent line, and then you would have to put in the 90-degree angle. What formula did you use, and we have used very, very often when finding the missing lengths of a right triangle? Pythagorean theorem, and we're going to use that here. So we have one leg squared, so x squared plus the other leg squared, which is going to be equal to 8. So 8 squared is equal to the hypotenuse squared. Now, this is where you have to be careful, because the hypotenuse is not equal to 7. That wouldn't make any sense, because the hypotenuse must be the longest length of a right triangle. And the 7 is marked only goes to the circle, not all the way to the other corner of the triangle. So the length of this hypotenuse, well, we need to remember that a circle is a set of all points equal distance from the center. So if this radius is x, then this part of the radius, or this radius, also has to be x. So the entire length of the hypotenuse of this right triangle is equal to 7, or x plus 7. Now, you can only use Pythagorean theorem to find the length of missing sides of a right triangle if you have two sides and you're only missing one side. And it kind of seems like we don't know the length of two sides of the right triangle, and we just learned SOHCAHTOA, which allowed us to solve right triangles in that situation. But we have a common variable that is helping to explain the length of this leg and the hypotenuse. So you can see when I wrote my equation out, I do only have one variable, so that's not going to be a problem. We have x squared plus 8 squared is equal to 64. X plus 7 squared, well, x plus 7 squared, anytime you square anything, you're just multiplying it by itself, twice. So we distribute this and have x times x, which is x squared, x times 7, which is 7x, and another 7x, and 7 times 7, which is equal to 49. And we get that x plus 7 squared is x squared. Adding like terms, we have 7 plus 7 is 14x, and 49. Okay, so now we have an equation to solve, and it has exponents of 2. So are we going to need a factor to solve this quadratic equation? Are we going to need the quadratic formula or complete the square? No, because when we try and combine these squared terms, we're going to subtract both sides by x squared, and you can see that 1 minus 1 is just equal to 0. So these x squares are just going to simply cancel themselves out. That means that I'm going to have an x on the right-hand side of the equation. For some students that's a little bit uncomfortable having the x on the right, but just remember to move everything away from the x. And that would be my heater coming on, so let me turn that off so it doesn't get distracting noise in the video. So keeping with the idea, we're moving away from the variable. We're going to subtract both sides by 49. Trying to find a different color so you can see the steps I'm doing. And 64 minus 40 is 24, and 24 minus 9 is going to be equal to 15. So we have 15 is equal to just the 14x is all I've got left, because the x squares canceled out and I just subtracted both sides by 49 to get the 15. We're going to divide both sides by 14 to undo that multiplication, and x is going to be equal to 15 over 14, which right off the top of my head is equal to 1.071. Okay, excellent. Now, if you're unsure that that's actually the correct answer, because this is a little bit of a difficult problem, then remember that you are just working with a right triangle, and the Pythagorean theorem allowed you to find that value of x. So that can become your check as well. So you can do, well, we believe that x is 1.071, so you can do 1.071 squared for this radius or leg of the right triangle, plus 8 squared is equal to, well, this portion of the hypotenuse is 7 plus an additional 1.071, so we get 8.071 squared. And when you check that, of course, you will get the right answer, or you will get the same answer on both sides of your Pythagorean theorem, proving that you've done your work correctly, because that was supposed to be a right triangle, so the Pythagorean theorem should hold to be true. Next two examples. Sup? Is this a tangent line? Yeah, man, whatever. Look, that's a right angle. It's got to be tangent line. Really? You're going to trust the picture? Does that really look like 9 if that is 5? Don't ever trust a picture. They're never drawn to scale. And even if they are, you still have to show your work. No, you are going to remember that if this is a tangent line, then that is going to have to be perpendicular. But hey, I just stuck my piece of paper on the corner. Each of those corners is 90 degrees. It looks like it's 90 degrees. All right, let's check it. If it's 90 degrees, then the two legs squared and added together must equal the length of the hypotenuse squared. All right, so we got 5 squared plus 12 squared, our two legs of 5 and 12, is equal to the hypotenuse squared, which is 9 and an additional 5 is equal to 14. All right, let's see. Well, if you know your Pythagorean triples, you already know this is going to be wrong. We've got 25, 5 squared is 25. We've got 12 squared, which is 144. And we have 14 squared, which is equal to 169. Well, excuse me, that would be 13 squared. 14 squared is 196. There, that's a little better. Let me double check, make sure I'm not doing it wrong. Yes, okay. And 144 plus 20 is 164, plus another 5 is 169. I know I was remembering that number for some reason. And that is not equal to 196. So not only, that means that this fails the check for it being a perpendicular angle or a right triangle, because the two legs squared added together does not equal the hypotenuse squared. Now, hopefully you remember your inequalities from right triangles, or the converse of your Pythagorean theorem, where we said, yes, they have to be equal for that to be a right angle or a right triangle. If the hypotenuse squared is more than the two legs squared, okay, if it is squared, then the two legs squared equals the hypotenuse squared. If you lengthen the hypotenuse without lengthening the legs, you're going to force that angle open more. So even though it's beyond the scope of the question, we've answered it. The answer is no, because this is not a right angle. But just to remind you of an old concept, that actually what we're showing is that this angle, though it was drawn to look like 90 degrees, is actually obtuse, because the hypotenuse squared is longer than the length of the two legs squared added together. Over here we have an inscribed circle. The circle inscribed in a quadrilateral, a four-sided polygon. And I want to use that one of those theorems I just had on the board a few minutes ago about that segments. If you have two segments and they share a common point outside the circle, then the lengths of those two segments are going to be equal. So we've got some tangency points here. One here, 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 and here. And I want to use that theorem to show or find the value of x and ultimately find the perimeter of this quadrilateral. So it looks rather complicated, and it really kind of isn't, as long as you remember that these segments from tangent to external point, tangent to common external point, that those segments are going to be equal. So I've given us an entire length of 5, 9, and 10, and this is the only place where I've given you the length of a segment from a tangent to an external point outside the circle. So we can just work our way around the triangle, and let's start, and we're going to do that this way. just because the way the information is given. If this length is 2, then this length is going to be 2. Tangent points, common external point, that is equal to 2. Okay, well this entire segment is equal to 5, and I just accounted for 2 of those units, so 2 plus what is equal to 5? Of course that's equal to 3. And then again, tangent point, a common external point, so these two segments are equal, so that is equal to 3. And keeping it up, we have an entire length of 9. 3 is already accounted for, so this length is equal to 6, which means this length is equal to 6. But this side of the quadrilateral is equal to 10, not 9. So 6 plus what is equal to 10? Well, that's going to be equal to 4. And that means that tangent point, common external point, those segments, one more time, have to be equal. So x is equal to 4. So we just solved for x, and then the entire perimeter is, of course, just adding the lengths of all the sides. So we have a length of 2 plus 4, which is equal to 6, plus 5, plus 9, and another 10. So what do we have? We have 6 and 5 is 11, 11 and 9 is 20, and 20 and 10 is equal to 30 units. We are talking about length, so make sure you use units, not units squared or units cubed, since it wasn't that long ago. We were talking about area and volume. One more example. For our last example, we have two circles, one with a radius of 18, another with a radius of 6, and we have some tangent lines connecting these points. You could think of this as a big gear and belt or chain set in a piece of machinery. And we have, again, the radius of 18 and 6, and we notice that the distance between the tangent points of A and B is equal to 40 inches. Using that information, how are we going to solve for D? What is the distance between the radiuses of these two circles, or the center of these two gears, if you will, if we had a chain or belt running around them? Well, we are not going to just do this in one step. Now, the math behind this problem is not extremely difficult, except you do have to call a lot on your past experiences with other geometric shapes and properties. Like, well, let's see, these are both radiuses, and this is a tangent, so what do we know about these angles here? Well, they're going to be right angles. And way back, we talked about parallel lines and proven lines were parallel. We have two lines that are perpendicular to the same line. So if two lines are perpendicular to the same line, then those two lines themselves are going to be parallel. So radius AD is going to be parallel to radius CB. So, well, we need to add a little bit to this diagram because we still, even with that extra bit of information, don't have enough information to find the length of DC. So what I'm going to do is, I've got these right angles and I've got these parallel lines then, so now what I'm going to do is I'm going to extend a line, another line from between the two circles, and hopefully that is relatively equal all the way across. And I'm going to do this in a parallel fashion. That lifts up a little bit, it's bothering me some. Okay, so if this length is equal to 6, then, and I do this so that these two lines are parallel, then here is 6. That means that this segment over here is also going to be equal to 6. So if this portion of this radius is equal to 6, then this portion left must be equal to, well, 6 plus something is going to be equal to 18, and of course that's going to be 12 inches. Okay, so now I'm a little bit closer to the length I'm trying to find of DC, but I'm not quite there yet. What I'm missing is, well, I have that length of 12, and if these two segments are parallel, then as long as I measure the distance between those two lines in a parallel fashion, I'm going to get the same length. So if I keep this distance of 6 all the way across, and I'm setting up a rectangle, if you will, or a parallelogram, but it's specifically a rectangle, then if this side is equal to 40, then this side is going to be equal to 40. Okay, so now I've got this triangle of DC, let me add another letter in here. I got A, B, C, D. Let's put an E in here. As I look at triangle DCE, I've got two sides. I've got a side of 12, and I stopped in the middle of my talking and forgot to add in the 0 there, and I have a length of 40. But how can I use those numbers to find the length of DC? Well, I set this up so that these lines were parallel, so that I could transfer this length of 6 from this radius over to this radius and break it up into two parts. So if these lines are parallel, and I'm setting it up to be that way, then when two parallel lines are cut by a transversal, then those corresponding angles must be equal. So if this angle is 90 degrees, as a radius and tangent line do intersect, then this angle here is got to be equal to 90 degrees, as long as the phone's not ringing, and I have set these segments up to be equal in length. Thank you. So what I'm left with is a right triangle, and that right triangle is going to be our answer. The DC is going to be the hypotenuse of that right triangle. So we're just going to do 12 squared plus 40 squared is equal to the hypotenuse squared of DC. I'm not going to put a mark over that DC because I am trying to indicate length, and I'm not going to try and do all this in my head other than, well, okay, I know 12 squared is equal to 144, and 40 squared should be 1600, oh, good, okay, is equal to DC squared. We have 1600, 1744. We're going to square root both sides to get rid of that power of 2. And that is going to equal 41.76 units. And, oh good, I just scribbled over my 41, made it look like a 9. Well, that is 41.76 or 41.8 rounded off. Does that seem to at least make sense? Well, I've got a length of 40 for this leg, I have a length of 12, and the hypotenuse does need to be the longest segment of a right triangle, and it is a little bit longer at 41 rounded off to 8. So it's a little bit longer, but yet not unreasonable. And that is the end of my last example. Of course, you could check this as well with old Pythagorean theorem. So hopefully you could follow this. Thank you for watching all these examples. I hope it helps you do your homework. So, I'm Mr. True. Bang! Go do that homework.